All right, welcome back, everybody. Today, I thought we could continue on a little bit with the spatial transcriptomics videos. So I had recently submitted a paper to Genome Biology where we had done some of this type of stuff that we'll be moving into next. So today, I would like to talk a little bit about cellular clustering in our samples. So you can imagine if we have a bunch of cells that are different types, we can see whether or not the different types are clustering with themselves. So that would be a univariate clustering, or if they're clustering with a different cell type. And remember, last time we had a handful of different ones. So if we look at the metadata, we can see if we go all the way to the end. For some reason, it's not liking that. Let's go all the way to the end here. We can see we have our unsupervised InSituType clustering. So that's what we'll be looking at today to see whether or not with univariate if the cells are clustering with themselves. You can see here I'm now running in Docker. So I'm still on Windows. Let's see if I can pull this down. Turn this off. I'm still on Windows, but the really nice thing about using Docker on Windows and then moving into the RStudio is that now we're able to use multiple threads. So whereas before Windows really limits kind of the multi-threading capability of RStudio, and using this Docker image here to run RStudio, now we can get multi-threading to work, which I'll come to in a little bit on why that's important. So I'll just walk through the script since it does take a while to calculate kind of what I was wanting to show today. So we have InSituType here. We don't really need that one, but we'll import it. Seurat, and that will help us with the object that we exported last time after running InSituType, and then tidyverse, which will allow us to do a lot of our piping and data filtering work. So the first thing that I did here is we don't really care anymore about the gene expression. We have our gene, our cell types. We can come back to the gene expression later when we want to look at things like pathway enrichment or gene set enrichment in particular cells. So we can do that at the cell level since we have the cell expression. But today we'll just import that object and then we'll extract the metadata. So the metadata is what I had shown here. That's going to have everything that we are interested in for what we're doing today. So we want this cell class here. So we have A through N cell class that we had assigned with InSituType unsupervised clustering. And then let's go back here. We have the X and the Y coordinates of the cells. So that's what we'll use to know their locations on the field of view. And then at the end, I had added in this here. So this is a unique combination of two different columns in that metadata file. So there's a slide ID number, so it's going to tell you which slide they had sequenced, and then there is the FOV. So let's see if I can find here quickly the slide ID column, and if I don't, we can always pull it. I don't see it. So here's our slide ID, so slide 1, and then if you go back to the beginning, we can see which FOV on this slide this is. So we have slide 1, FOV 100, for example. We're just creating that extra column. That way we have a combination of the slide and the field of view to make sure each sample is unique here. So I saved that. That way we can always just import the metadata again instead of having to import that object, because we remember last time that object is very large. So saving just the metadata, it's just a data frame here with 188,000 rows for all of our cells. That'll save us a lot of time. And then what I did is I just cleaned our environment with removing that Seurat object. Now we can move on to the actual data preparation for what we'll be running today. So we'll be running a function within the Spatial Time package that I wrote that's on CRAN. There's code in here too if you want to download it. And what this package does is it allows you to look at clustering of point patterns of biological data. So we have points, our X and Y locations of our cells, and if we use that and pass it into the spatial time package, we can look at the clustering of, say, this cell with this cell, for example, and get a metric for that at different radii. So what I'm doing is with the metadata, to get just the spatial data. We don't care at all about all of the extra metadata that is in that data frame. We just need the unique ID that belongs to each sample, which we had created, that unique FOV. And then we want the X and the Y location of the cells, along with the class of each of those cells. With that, then I created another column here called positive. So it's just going to add a 1 for everything. And after that, what I can do is spread it out. That way, each of our different cell classes gets its own column. So there's a column of A, B, all the way through N. And where the cell is positive, there's a 1. And if that cell does not belong to that class, then it is a 0. So if we look at this, we can see all of these cells here are positive for class A, or the annotation from InSituType as A. And if we scroll down, we'll get to B's. Maybe. Oh, I have to reopen it up. But yeah, so the moral of this data frame is that we have each cell is in a row. Let's go here. Each cell is in a row. So this first FOV, we have all of our A's, and if we scroll down far enough, then we can see, okay, now we have all of, from here up, these are all cell type A. From here to here, all of those are cell type B, so on and so forth, all the way to N. And there's actually only one cell that is positive for N. So when running any of these summary functions, like today we'll do nearest neighbor G, they're probably going to be removed for every single FOV except, or even this one. So you can't do clustering with a single cell type. Let's look here, M. So M's even got enough that we can get some curves out of it. So from there, what spatial time needs is a list of these data frames, or a list of data frames, each one corresponding to a different sample. So if we scroll all the way back up here, we have, so here, slide 1, all of this, we want this, oh, there's kind of a lot here. All of slide 1, FOV1 to be in its own data frame. And then what we want is the next one to be in its own data frame. So if we use split, and we can split on that unique FOV column that we had created that is sample specific, remember. So all of slide 1, FOV1 in this column is the same sample. So if we split that big data frame on there, we can now look at spatial list. So we can see slide 1, FOV1, there's 424 cells. If we open this up, we can see that now we have that big data frame split just to include slide 1, FOV1. So this split function is really handy for doing that. Now, what spatial time needs also is a summary table. So here we have a table for the cells, so each row is a cell. But what this summary table is that each row is a sample. So there is a row, one row for each entry in your spatial list. So here I just have cell types, which is A through N. If we go ahead and run this, we can see here A, B, blah, 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 all the way through N. And that corresponds to the columns in our spatial data that we want to summarize. Remember, as we have A through N, we want to summarize our cells. We come back over here. What I'm doing with this lapply function is going through each spatial data frame in our spatial list, so each one of these. I'm grouping by our FOV, and that's just to maintain the unique FOV as a column in our output. So if we go back to our spatial list, we want unique FOV to be an entry, a column, in our summary data. And then we're going to summarize. So we need our total number of cells. And what that's going to be is just the number of rows, so 424, using the n function from dplyr. And then we want to summarize across all of our cell types. So we have A through N. What we want to do is we want to take the sum, because we have ones and zeros, ones being positive. We want to summarize all of those columns and get the number of cells for A through N. And then after that, what we can do is we can take all of those cell types again, and we can find the proportion, or the percent, of the total number of cells that belong to that particular cell type. So we'll get the count, which is going to be the number of cells that are positive for A, for example, in our data, each of our data frames, and we'll get the percent of cells that are positive for A in each of our data frames. So let's go ahead and look at this summary data frame. And I forgot to mention here, so this is going to return a list where each element is a one row data frame containing the above mentioned columns, and then we're going to bind that together. So then we're going to get one data frame in the end with the number of rows equal to the number of fields of view from our Cosmics data, and each column is going to be some summary of that particular sample. So let's look at our summary DF. So you can see here, slide 1, FOV1, we have 424 positives, or 424 cells in total. 39 of the 424 are cell type A, which comes out to be 9.2% of those cells. We can see kind of the distribution for all the different cells, and N is that very rare one. It looks like G is very rare as well. But we have a row for each one of our samples, our fields of view, that we have our Cosmics data for, which is great because now we can see, if we wanted to, we could plot box plots and see the distribution. Perhaps there's far more cell type A than we would expect if we knew the phenotype of cell type A. So that's where the other video for InSituType might come in handy if you want to apply a signature, a known gene signature for single cell data to get the phenotypes. But coming back here, awesome. Let's go now and add a column for patient ID. So there's 3 data types that go into the spatial time package. 1 is the spatial list, 2 is the summary data frame, and the 3rd one is clinical data. But there's got to be a way to link them all together, right? So our spatial data has that unique FOV column. So spatial list, we have our unique FOV. And our summary data frame will have unique FOV, like we had looked at. But we also need another column that will tie this to our clinical data. And when we're only working with one sample, so here would be one unique FOV per patient, then it doesn't really matter what that ID in that other linking column is. But in the cases where we have multiple samples from a patient, we can't use the unique FOV to then link to our clinical data. It's because our clinical data would be one row per patient. This would be one row per sample. So there would be a column where, for example, these 3 would be patient 1. And we would have to specify that. So here it's not critical, but in some cases where you have repeated measures, it is important. But here, since we don't have repeated measures, we're just using the unique FOV as that linking column, and we're going to call it patient ID. So if we go back to here, we can go all the way over, and patient ID is just a repeat. But in the event that you have these 3 of the same patient, here you would have patient 1, patient 1, patient 1. And in the clinical data, you would have one row for patient 1 that describes that patient. Great. So now if we look at our clinical data, what I'm doing here is just pulling out information that may be pertinent later on that we can compare between groups. So we have our unique FOV, which here we're just using to reassign to patient ID. That way we can link clinical to summary, and then summary is linked to spatial. But we have all of these other sample level features that we are putting into clinical. So it's not any spatial information. So there's not going to be the X or Y coordinates of each cell. This is sample level information. So if we scroll over, basically most of this is going to be the same except some of this QC data here. So we have the number of transcripts that were identified in total, negative probes, so on and so forth, the average per cell, the negative average per cell. That might be all something that later on we can go through and compare between the different groups. So perhaps there are associations that maybe are not sample specific or like a tissue specific, but all of those on a particular slide. So if we look over here, we should have slide ID. Maybe slide ID has far more transcripts being assigned in slide 1 than in slide 2, for example. And that would just be a QC thing that might flag samples belonging to a particular slide. But this is all sample level information. So in the big spatial data table, metadata table, these are repeated. So you can see here, unique FOV, like this is repeated for the same sample. And we just collapse that down for our clinical data. So now we have one row per sample. Awesome. And the row names are meaningless here. Cool. Okay, so now we'll move on to using spatial time. So what is spatial time? Let me see if so spatial time actually stands for spatial tumor immune microenvironment, and it was designed to work. It was designed to run on multiplex immunofluorescence data. So you'll see a lot of the designations called like MIF, multiplex immunofluorescence. But since we have X and Y locations, we can go ahead and apply this to our CosMx data as well. So let me see if I can pull up the help page here to show all the functions. Here we go. So this does not look like the most updated version. Interesting. Anywho, so in spatial time, there are a lot of functions that are contained to let you do clustering analyses on your point data. So you have X and Y locations for all of your cells. You can then look at clustering of them all. So you can see here we have point data for this particular sample, and then you can look at clustering. So if we scroll down, we can compare clustering between the different cell types. We can compare clustering between the different samples, so on and so forth. So today what I'm going to show is using spatial time to look at the nearest neighbor clustering of each of our cell types. And then we could go on later and associate that with some of those features in the clinical data. But so in order to create the object that spatial time depends on, we have our clinical data, our summary data, sample level data, and then our spatial list that contains all of our cells broken down into samples. So the patient data is what's going to link our clinical data and our sample data together. So we had to create that extra column like here called patient ID. And then our sample ID, it links our spatial list with our sample, our summary data. So that's the sample level ID here. So in our case, these are going to be the exact same. We just have to create two different columns. After that's created, we can go ahead and look at it. So we see here that we have 329 patients, patient ID. 392, excuse me, samples. So it's going to be our unique FOV. So those are the same. And then since we are creating this, all three of these from the same data, they'll all have spatial data. So we have 392 spatial data frames as well. And that's our spatial list. So this is kind of just a double check to make sure that we have everything that we're expecting. I don't think this installed the version. The output is gonna still work. But I don't think this is the most up-to-date version of the package. Anywho, the most up-to-date version of the package should be 1.3.4-2. Let's go back. Spatial time. Packages, spatial time, 1.2. Nope, so this is an old version, but in either case, it will do what we want. The newer version is just much faster, which might explain why this took so long. So we have our object created. We've looked at it to make sure that all of our samples are there. So next, what we have to do is we have to decide what radii we want to measure around each of our cells. So you can imagine if we want to see clustering of our cells, we can look at really, really close. So a radius of, let's go ahead and plot this one so we can see the cells. We can look at a radius really, really close. So maybe 110, for example. We can't be closer when looking at our point data than the radius of a cell. So if a radius of a cell is 10, 2 radius, then 2 cells can't be closer based on point data than 20, because the distance from the center to the edge and then the edge to the center where the points would be at minimum 20. So when we look at the output curves, there will be a flat line at the beginning before seeing the actual curve. But we need to find out what range we want to actually search for clustering of our cells. So here what I'm doing is just looking at the minimum and maximum difference in the X direction and in the Y direction for our entire field of view, because we can't search from 2,000 to 4,000 as a radius, because then anything close to the edge is just going to be mostly outside. Like there's nothing out here, and then your edge correction will take over. So looking at the range will give you an idea of kind of the limit that you can search for your radius. So let's look at the ranges here. So I took the for each unique FOV with our spatial data, looked at the difference between the largest X value and the smallest X value, and then largest Y value and the lowest X value, and that gives you the size of your field of view. Just looking at our range. Here I have it sorted on the X range, so this is going to be the smallest field of view limit that we have in all of our data. So with 1,400, and then the max is over 4,000 for both of them. So we need to stay well within this. So this is going to be the entire size of our field of view, but we need to remember radius, and then we need to stay well within this. So I picked a radius of 200, which might be a little small, so we could actually go ahead and plot this one here and see how this looks. Field. So let's pull this out, and then go back to our range so we can see the shape of this guy here. So this one looks really funny. I am not sure why this is the field of view that they have. Perhaps it's tiled to another one, but when looking here, we need to stay well within this 1,500, 1,400 boundary So what I had selected was R of 200. It might actually be a little low. We could do probably an R of 250, which means an entire search diameter around a cell of 500. So this cell here, it would probably look to 500 and then 1000. So we're looking at fairly close small scale clustering with an R of 200, which is fine. So I have some notes here. So I have mentioned this here. We'll have to stay well within our 1400. And we have to remember radius will actually be on both sides of your cell. So R of 250 will kind of put you at an entire circle diameter around a cell of 500. So for permutations, there are certain functions within the spatial time package. Let me see here if I can actually install a more recent version. Spatial time. There should be a version of spatial time that is available. The package will be installed. No. That is on CRAN right now. That is 1.3.4. It's also on GitHub, so actually we can try to install it from GitHub. Proceed, no. Dev tools, is that installed? So as that's going, okay, I'll keep talking here, and then we can look at the different functions, and I can say the difference between the permutations, and then there's an exact measure as well for univariate Ripley's K and bivariate Ripley's K. The number of workers, this is where at the beginning I was talking about how the number of cores on Windows is often limited, and that can be a hindrance when you have to do some of these very compute-heavy or time-consuming things. You can imagine with a single core on Windows, it would take much, much longer than 17 minutes versus 16 cores taking that long for 100 permutations. The newer version of Spatial Time is much faster. Hold on, I gotta install this into our Docker environment. Go ahead and get that going here quick. Yeah, we'll worry about it later. Yeah, it just takes way longer with less cores. So that's why this Docker is really nice. So the particular function that we're looking at today is the nearest neighbor G. So it is a cumulative distribution function if you don't use an edge correction. Ideally, at some radius around a cell, no matter, I don't know, the direction that you're going, at some radius, all other cell types of the same. So at some radius here, all A will be within that R, that radius. So it should be up to 100. And the way we can look at that when we get down. The way to interpret this is at a radius of whatever 50% of A are that far away. So we have our range that we selected before. M names, this is the marker names, and we have our cell types, so A through N, and we'll go ahead and calculate this nearest neighbor G statistic from 0 to 200 radius, so it's probably pixels, for all of our different cell types. The edge correction that we're using here is reduce sampling. There's a handful of them in there, so if we go here, I think there's also HAN, which is Onish. Nearest neighbor G. The edge correction. Yep. So we have a couple different ones. You can also do none in the updated version of our spatial time, and it will not do any edge correction, which is sometimes easier to interpret. Keep permutation distribution. So if you have a lot of permutations and you set this to true, for each radius, each cell type, each permutation, there will be a row. So you can imagine Compared to this output here where we have it set to false, there will be 100 times more rows in the output with keep permutation distribution set to true. And that can often be helpful if you want to look at significant clustering of your cells versus just looking at the difference between the estimated complete spatial randomness measure, which is the estimation where all cells are randomly assigned a value of A, for example. Instead of A falling here and here, A can be randomly distributed. So you're measuring the complete spatial randomness of your sample in particular, and which is the novelty of spatial time. It adds that functionality. Overwrite, what that's doing is it's checking whether or not you've already run nearest neighbor G in the multiplex immunofluorescence object, the MIF object that you have. And if it is there, it'll just replace it. Here, since we don't have anything calculated yet, it doesn't matter if it's true or false. It's not going to do anything. And then we have our X and our Y locations. So we have to specify our X and Y locations here. So after running that, I just save the output. And then what we can do is we can visualize this. So in our new object, let's open up here, there's this derived, which will have all of the derived metrics in it. And if we open this up, we can see that we have our univariate nearest neighbor G, and we have a data table with 1.1 million rows. So they can get very large very fast. And that's a function of the number of radii that you're measuring, the number of cell types, and the number of samples. Awesome. So if we pull that out and go add it to nearest neighbor G, we can take the head of that, and we can see here we'll have all of our samples in the unique FOV. We'll have all of the markers, so A through N, all of our radii, so 1 through 200, because 0, you can't measure 0 radius around something, so that's removed. Our theoretical complete spatial randomness is a function of the number of cells that are positive on our particular sample here for G. So that's added in here. And then we have our permuted complete spatial randomness. So this one is a little bit more trustworthy because for the theoretical, we can see that we're already having values here, albeit small. But for our permuted complete spatial randomness, like I had previously mentioned, around that cell, let's see if we can open this up here. Around that cell, you're not going to have any positive cells within 2R of it, right? So if we go here, we can see 34. So the nearest two cells that we have, it's actually here, 31, 30, we'll call it 30. The nearest two cells that we have possibly a radius of 15, so 2R. So there's nothing any closer than 30. Cool. So then we can look at this. So for slide 1, FOV1, we have all of our markers, and then we have all of our radii that we can plot along the x-axis, and then along the y-axis, we can plot our degree of clustering permutation. So what the degree of clustering permutation is it's our observed. So how clustered is A in reality, the true clustering of A in their real positions, minus our permuted complete spatial randomness measure. And that is specific to each sample. This permuted CSR will change for each one of your samples because there's a different number of A positive cells, and then the locations of cells are not going to be exact between samples too. So we have our degree of clustering permutation, and we can plot that along the y-axis, and we can color it based on our marker. So let's go ahead and do that here. We have it saved as some plot already, but we can go ahead and plot this. We can see that there were 1,000 rows, so 5 markers that did not have enough cells. So we can look back at our summary DF that did not have enough cells in order to calculate the nearest neighbor G spatial statistic here. And those are probably E, G, I, J, and N. There's just not enough there to calculate clustering between cell types, between cell locations. We have our 5 removed with 1 to 200 radius, equaling 1,000 rows in our final output. And what we can see here is that the degree of clustering, like I had mentioned, is our observed minus permuted. And we have this band here at the beginning where no 2 cells are within this radius of each other. And then from there, if we are positive, that means our observed clustering of our 2 cells, so here either B or C, is much closer than it is if the cells were randomly distributed on our sample. So we can see that our B and C we can call clustered here since it is positive. And then it falls off around R of 100. It crosses over into actually being negative. So this is more dispersed than we expect if B was randomly placed on our field of view. So this might be interesting to look at cell types. We can see here potentially K and L, K and M something. These two are always clustered regardless of the radii that we're looking at here. So up to a radius of 200, these 2 cell types are clustered. Now, it might be interesting to look at what these 2 cell types are. Potentially, they are cells that are always going to be found close to each other for biological reasons, and we expect this to happen. Whereas cells like this, D, is actually always negative, so they're farther away than we expect if they were just randomly placed. They have some repulsion happening between them where D does not want to be close to D. Then we can also look at the point plot for this. Let's go ahead and look at FOV1. If we see D, it's kind of this, well, it's going to be really hard. These here, D, D, D. Maybe that's F. In either case, let's go ahead and plot these next to each other. Explore it a little bit more. So we have our purple, and it would be helpful to make the colors the same, but we have our purple here, which is K, and if we look at K here, it's that dark blue. We do see it much more clustered than if they were just randomly placed all over this. So that's good. That is biological because K is in this upper left-hand corner and not so much, there's a couple down here, but not so much in this lower right-hand corner. So that's biological. Also, we see, hard to tell, L. We see L here that is also clustered with itself. We can see that where there is an L cell, there is a high probability of there being another L cell very close to that, which is pretty cool. Even down here, you can see a straggler here, but we have an L positive, and then there's other L's around it. L positive, another L, 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 which is really cool. But then with this data, if you had something like a clinical annotation of this, you know that this is from a patient that had received immunotherapy, for example, we could select a radius, I would say a radius of 100, and then look at K at that. So we have our K value. Is there a difference between samples that had received immunotherapy or chemotherapy? K clustering value at a radius of 100 between those that have and those that have not. That could be very interesting to see. And it's something that tissue might be informative if it's a tissue type cell, but mostly informative if it's an immune cell, because the immune cells are going to be infiltrating the tissue. So if we have a much higher proportion of cells that are CD3 T cells that are showing much more clustering after immunotherapy than before immunotherapy, we can see that the immunotherapy is having some impact on bringing T cells together in the tumor. Additionally, we can look at those that responded versus those that didn't respond. At a radius of a radius of 100, compare between those that are responding to treatment, those that are not responding to treatment. Are those that are clustering more likely to respond to immunotherapy than those that are not clustering? And that might be a prognostic marker that patients, when they come in, you could sample their tumor, see whether or not there's high clustering of a particular cell type. And if they do display this high amount of clustering, they can be more confident that the patient will respond to immunotherapy. In the future here, I'm able to install this. Go to, I can show you the Docker window that I have here. Terminal, let's go ahead and paste this in and see if we can get this installed. We'll try to get Spatial Time installed again. Or dev tools, install packages, dev tools, because I want to show you the updated version of Spatial Time and all of the functions that are inside. The current version that is here, I don't think has the exact measure for Ripley's K, which is unfortunate because for those that are using Ripley's K, you don't need permutations in order to calculate that degree of clustering anymore. You get an exact sample-specific measure of the complete of the randomness measure. So let's do dev tools now, and then we can install GitHub, Ripley Lab Spatial Time. See if it'll install. The version should be 1.3.4 or -2.2. See here, we added in some other functionality and speed. There you go. Spatstat Explorer is not available. Okay, so I have an older version of spatstat apparently that it's not liking. But moral of the story for this particular video is we have spatial clustering of our cells. If you have any questions, I know this is a super long video, but I wanted to walk through everything here and make a little bit more sense. Let me see if, if you have any questions, leave them in the comments. I apologize for being a long video, but this is something that can be very, very useful when looking at the CosMx data. And now that you have your phenotypes, you can see whether or not those phenotypes are clustering in your samples. So yeah, thanks for watching, guys.